Let us start today's session. So, welcome all of you for this live session for week 5 of Smart Grid Basic to Advanced Technologies NPTEL course. So, we'll start with a brief overview of week 5 and then we will discuss some questions and then you can ask your doubts. So, these are the deadlines for assignment 5 and 6. You have to submit the assignment 5 by tomorrow. And assignment 6 by September 6th. You can find the recordings for the live session on this link, which is also available on the portal. Let us go through overview of week 5. In week 5, we discussed about microgrid, especially the iambic detection techniques and basic protection principles. We'll start with microgrid first. So what's a microgrid? It's a new concept and a part of smart grid. Now there are another concepts such as nanogrids also, which is a smaller part of subsection or subpart of microgrid. So microgrid, when we connect different types of DERs inside a distribution system, which can be self-sustained system, and such a system is called can be called as a microgrid. So it is a self-sustained system. Even if it is disconnected from the grid, it can still supply the demand. So that means the microgrid has its own generation. It can be renewable as well as non-renewable. But now our focus is towards renewable generation. So we want to achieve, for example, India's target is to achieve net zero by 2070. Similarly, other countries have also set their different decarbonization targets, and to achieve those targets, renewable based microgrids are going to be an important part of the distribution system because they are not only help us in achieving these targets, reducing pollution and all that, but also help in automating things, making the system more reliable and ensuring adequacy of supply. So these are different types of classification for microgrid which I have taken from this paper which I have mentioned in the reference. Microgrid protection challenges and mitigation approach, a comprehensive review. So it's a paper of 2022. You can go through it. It's a good paper, and you will find very good different types of challenges and mitigation approaches which are available for microgrid. It's an IEEE access, and after the class, whenever you get time, you can go through it. So starting with size, if we see, there can be three types of classification. As this is as per this paper, there can be other classification also, but this is the most widely acceptable. So less than 10 kilowatt, it's small than between 10 to 1 and more than 1 megawatt. So you can see in the lecture also you have seen that there can be one single home microgrid or single user microgrid, then there can be single feeder microgrid, there can be a substation, entire substation can be a microgrid. So these can be different levels. So within a microgrid also there can be a smaller microgrid. So this is smaller and this is a part of this feeder and this is a part of this substation. These are different levels, and depending upon the condition, depending upon the prevailing fault condition, we can isolate different parts within a distribution system, and they can be self-sufficient, self-sustained. Even a single home, if it is isolated and if it has a PV or wind source, then it can also work. It can still continue to supply its load, serve its loads. So that is possible. Then we can have three types of configuration, or we can say architecture of microgrid. We can have DC, AC, DC, and hybrid AC, DC. In this week 5, we have only considered protection challenges for AC microgrids. But in future, in subsequent weeks, we will see DC microgrid, different architecture of DC microgrid, as well as hybrid AC DC microgrid and their control strategies. Then there can be these different types of other classification. This is based upon the requirement, or the, you can say, the nature of the usage. So there can be residential consumers, industrial, commercial, and agriculture. So they can also combine to form one microgrid. So this can be a different level of microgrid. So this is another type of formation. Then there are three modes of microgrid. One is grid connected mode, then islanded, and third is this transition. So transition from islanded mode to grid connected mode, which we also call as restoration of power, or from grid connected mode to islanded mode. These two transition are possible. So both will come under this third category. Then, based upon type of source, different types of sources which are available within a microgrid, you can have these different three types: renewable, non-renewable, as well as hybrid. You can have both these two, combination of these two. Just as at present we have, so we have solar PV, wind. We don't have at each home, but we may have. Uh, but we still have diesel generators. So even within a campus, you can say education institutions, just we have solar rooftop, and we also have diesel generators. So that is example of hybrid. So both renewable as well as non-renewable are there. So in non-renewable, these two are generally used: diesel generator or small gas turbines. For renewable, we have wind. Now small wind turbines are also being produced, for which can be used by a single residence. So we can have install them just as we have rooftop solar panels. We can have these rooftop wind windmills, also wind turbines. And these solar rooftop, then micro turbines, biomass, fuel cell, and hybrid. We can also add EV here if it supports vehicle to grid capability. Then EV can also act as one of the source inside a microgrid. But these are the major sources. EV will not always be available, and it will also depend on its state of charge, how much charge is available within the battery of the car. But in backup, as a backup or in emergency situation, EV can be used. Then these are two different configuration for not just microgrid, any kind of distribution system. They are radial. So here you can see it's fully, this is example of radial. So we have a single feeder directly going here. This is one feeder, and all the loads are connected on this feeder. So this we call as lateral. These are laterals. These are laterals. But this is a feeder. So one substation can have different feeders. So here we can have multiple feeders also. One feeder can go like this, one can go like this, and they can have different laterals. But all these are radial only. Power is going like this. There is no interconnection in between. Suppose like this. These two are not connected, or this is not connected here. Such type of interconnections are not there. So it's a radial system. So convention still we have a radial, but in somewhere different, such as education institutions or different campuses, townships, they have their ring system or meshed system. This is example of a meshed type of distribution system. So here we have a mesh. This is a mesh. With such type of system configurations are also possible. So that this can be opened in case of fault, and still you can supply the load using this path, or even this can be opened. So this is normally closed. Normally it is open, but it can be closed also. And these are the protective devices, all the relays. And in convention system, in radial system, because we used to have this power flow only in one direction, there were no distributed generators available in conventional distribution systems. So there was only one source which was providing power to all the nodes. So power flow was always a unidirectional flow in one direction. But now the power can flow. So suppose for in conventional system, if there is a fault here, if there is a fault here, if there is a fault at any point, the only current which will be feeding that fault will be through this utility substation from substation source current. But now because of this DER, if there is a fault here, then there can be one current from here, one, and all these other distributed generators, they will also supply current to this fault F1. So as a result, we no more have unidirectional current. So in this feeder, we can have current in both the direction. Everywhere we can have bidirectional current power flow, and because of that, protection system has to evolve. It has to adapt itself, change itself to accommodate all these changes. So these were the things which we discussed. So these are some challenges for the new. Although we are increasing these renewable or different types of DER, but they are also creating problem with for our existing system. So one of the important components of any system is protection. So they are going to pose numerous challenges for the existing protection system. So now let us go through the week, this overview first. So we discussed these two main topics. One was anti-islanding detection techniques, and then
Excuse me, sir.
yes,
So let me ask one doubt, sir.
okay,
Sir, actually, in the radial system, in the point of protection, it's good. But in meshed current system, if there is any fault existing, even if I had to operate the relays, islanding is not going to be possible. Anyway, the particular part has to carry the load always. Am I correct, sir? In that situation, how we have to make islanding conditions?
in case of a ring system, you're saying.
Yes, sir.
So if we have a ring system, I'd say And this is also connected to the main grid. And we can have DERs here. We can have it here. Okay, so entire this is a ring system. If there is a fault here on grid side, you can open this circuit breaker and this entire ring system will be islanded. And good thing with ring is if there is a fault here, you can isolate this part. Sorry, you can isolate this part, and still other sources can provide the load. It can serve the load. The ring is the most reliable system. Ring means, but it adds to the cost. So that's why we generally don't. We, we use a ring means only when it's a critical system. We anyhow whatever may be the situation, we need to supply the load. So generally we use meshed system in the distribution system. Those we have in India. Generally we use this mesh system. So they operate in radial fashion, but if required, they can form these meshes are there, but they generally operate in radial fashion. Whenever there is any kind of fault, they will just reroute the power. So meshes are existing, but we operation is in radial fashion, and whenever required, we can use those meshes.
Yes, sir, of course. Anyhow, we obtain the power supply always, even if there is any fault existing. Am I correct,
Yes.
sir? In that situation, nearby conductors are getting overloaded, sir.
Hmm. Yeah, that may happen.
May not happen.
Yeah, that might happen. That is possible.
Okay.
That is
Yeah,
possible.
again, it is overloaded. Again, some cumulative function is going to be happen. Again, it will be lead to fault,
Yeah, but generally whenever we design the system, so it is designed keeping in view that if there is contingency, one or two line goes out, then still we are able to maintain the line flows within their limit. But
Thank you,
sometimes
sir.
it may happen that even uh,
Understood, sir.
whatever what you are saying, it's a cascading failure that may happen. But we try to avoid those situation at a planning stage only. But if it happens, then we have to curtail. We don't have any choice. We have to do that.
Thank you, sir. Thank you, sir.
Okay. Okay, so let us move ahead. So we discussed this. We'll start with this anti-islanding techniques. So we have already discussed these 3 points that we can have these three modes of operation, and this is done. Advantages of microgrid is we have also seen this. Then necessity of islanding detection. This that. So can you tell why do we need to know this islanding detection? What why do we need to know whether the microgrid is in islanding mode, islanded mode, or grid connected mode?
to make the relays function properly.
Correct. Yes, because uh, we'll see. This is also one of the challenges of these new, because of these introduction, increasing penetration of DER. That the number of DERs, location of DERs, penetration of DERs, all these things, even the mode of operation of the microgrid, all these things affect the protection system. The relay settings will change. Will have to change. Otherwise, they may lead to mal-operation of different types of relays. So inside microgrid, we have this microgrid controller, central controller. So central controller will give commands to all the relays. So for that, it need to have all the information, and those information include the relay settings, different types of relay settings, and then mode of operation of the microgrid, that also need to be known. Then only we can operate the relay in the desired fashion. So that is why LND detection is very important. Also, one thing was explained for protection purpose, for safety reasons also it is required. If suppose there is a fault here, this is the main grid side, and then here we have our microgrid, and this is PCC point of common coupling. Suppose this relay is open, there is a fault here, and if there is a fault here, and we don't know the microgrid controller doesn't know that there is an islanding, so there is a fault and it should be islanded. If this information is not known, if any person is working here, then they may get shock because we have different types of distributed generators here and they can feed this fault current. So, but if we know that yes, there is a fault on the main grid side and the microgrid needs to be islanded, if we detect this thing, then microgrid this can open. And everyone can know what's the status. So different types of circuit breaker status, relay settings, and the mode of operation of microgrid. All these inputs are given to this microgrid controller, and based upon that, it is able to take appropriate decisions. So it's an essential input for the controller, and we will see in the subsequent weeks also. And because of uh, different types of new types of converters also, this mode of operation, knowledge of this mode of operation is very very important. The type of inverters that we are using or converters which we are using right now are different. They are voltage source converters, but in what we are trying to do, we are trying to make grid farming converters. So that will come in the subsequent week. We'll see the importance of this information. These are the two types of islanding. One is intentional and one is unintentional islanding. So intentional islanding is it's already planned one. We already know we want to do it. It's anticipated and a systematic in a planned fashion. We separated the microgrid from the main grid to avoid any kind of major breakdown. So this can be because of these different types of reasons. So to overcome blackouts or even cascading failures, if the operator knows that there can be different type, this cascading failure is a possibility. So a part of the network can be separated, isolated from the main grid to avoid the frequency deviation. So, and another main important thing is system maintenance. This we do on a regular basis. Generators are taken out of the system. So, for that purpose, small part of the system, even in distribution system, we see, especially during this Diwali season, the scheduled maintenance. It's throughout the year, but during Diwali, it's there because everyone wants electricity. No one wants the electricity. Should not There should not be any outages, especially during Diwali. So they they plan it before 2 months. They start planning they do scheduled maintenance. So they will isolate different parts every day and carry out the maintenance so that there is no outage on that in that week. So that is system maintenance. And then purposeful load curtailment is there. We know that, just for example, in rural areas especially, the agriculture feeders are there. So in 24 hours in some states, especially in Rajasthan, I know that they have a roster system. For 24 hours they have divided into three groups. So divided into four groups. No, sorry, three groups. 8 hour or even 6 into 4, yeah, 8 into 3. So they divide 24 hours into 4 period of 6 hours. So they will give electricity for 6 hours to one feeder, then they will switch it to another feeder. So in a circular fashion, they will do it. For 6 hours, they will give three-phase supply so that they can carry out their agricultural work. Agriculture pumps are there. So that is a type of load curtailment. It's also systematic, already planned. Then there can be temporary faults also. So all these are intentional. Then there are unintentional. That is the main focus of this week. Without any planning, without any prior information, there is islanding. So this we want to detect. Because as soon as intentional, we already know we have planned it. So we can monitor everything. But unintentional is important to know so that we can make changes as soon as there is any kind of disturbance to avoid any further problems. So because of fault at main grid side or system failure, or there can be human errors or natural disasters. All these, the most common is this fault at main utility side. Natural disasters are also, but these are not on a daily basis. They are. This will come under resiliency. So our entire system, microgrid, even the main grid has to be resilient against all kind of these natural disasters. Wildfires, especially in India. In India, the most common disaster, especially on the eastern coast, is this these cyclones. But if we see European countries or especially America, they have their natural disasters are very common, especially cyclones, these hurricanes, and then wildfires. They are very common. They are becoming, their frequency is increasing. Therefore, they are very much into this resiliency of distribution system. They are working a lot in this area. How to make the system resilient and how to bring it back once a disaster has happened. So that is restoration of power. It's a very big challenge. How to do that in a very efficient way, as quickly as possible, and as in the cheapest manner, most economical manner. So for that we have to plan in advance, and also corrective measures have to be taken as soon as there is any kind of these disasters. So these are the different types of islanding detection techniques. So we discussed four different types of islanding detection techniques. One was passive, active, hybrid, and communication based. In passive, there are these different types of further division. One is conventional, signal processing, and AI based. So conventional techniques were discussed in detail. Some of them were discussed. For example, this Roorkee was discussed. Voltage and balance, impedance was also discussed, and this was also discussed. So these are different types of techniques. So different types of measures, parameters can be measured on the. So PCC, he can measure these parameters and then continuously monitor them. So these type of techniques are these are economical. That's why most widely used. And there is no power quality issues here. But the problem here is of larger NDZ. What is NDZ? Do you remember?
It's a non-detection zone.
Non-deduction zone.
So what is it? What?
Variation of P and Q power is not detected by the relays.
Yes, this is one where we are. If even if islanding occurs, we are not able to detect it because the mismatch is lower. Because so these techniques they need a higher mismatch. If there is zero mismatch, they cannot detect islanding. So that's a disadvantage of these techniques, uh, conventional techniques. So there are no power quality issues because we are not injecting or creating any kind of disturbance. We are simply measuring these parameters and then comparing it with their previous values. So especially in this, so one which was discussed was Roorkee, rate of change of frequency. So what we do here, we estimate this frequency on the digit terminal to decide whether there is islanding or not. Right. So rate of change of frequency we are monitoring here. How frequency is changing with time. But here with passive technology, these techniques problem is of deciding the threshold. How should we decide the threshold? That is also a concern. And these threshold may also change depending upon the sampling frequencies. And that we have also discussed, we have already discussed that they need a minimum amount of power mismatch beyond below which they cannot detect. And they are also affected by the load type, generator inertia, all these things. So that is why they have these inherent demerits. The rate of change of, let's say, angle, what we will do, we'll calculate V and I. We can measure V and I at the TG terminal and then calculate the phase angle, phase difference between this voltage and current. Then we have to calculate d delta by dt. So you can say it's in everything is discrete domain, so it's delta k minus delta k minus 1 and tk minus tk minus 1. This will give us, let's say, certain value delta. And if this delta is greater than the threshold which we have specified, then we will say yes, islanding. This is a case of islanding. So islanding is detected. So this is the basic principle which is used in all these in this conventional technique. So just instead of delta, we have to change different values. It may be voltage, it may be, so it can be frequency, can be voltage, then impedance also, and voltage unbalance also we can check. So in voltage unbalance, we will see V2 by V1. Voltage unbalance is given by negative sequence voltage by positive sequence voltage, and this we can compare with the threshold. Then there are these signal-based signal processing techniques. There are different types: is wavelet transform, S transform. They have this lower NDZ. That is their advantage. Then the conventional, and in all this passive, there is no power quality issue because we are simply measuring. We are not injecting anything. But here the problem, disadvantage is higher signal processing requirement, higher computational requirement. Our existing processor which we are using, we don't, they may not be able to provide this much computational requirement. We'll have to replace them. So that will add to further add to the cost of the existing system. So that is a demerit of the signal processing based technique. Then for similarly for AI techniques also, there are several AI techniques: artificial neural network, support vector machine, fuzzy logic, this long short term memory, and convolution neural network. All these are there. They also have lower NDZ, but problem is huge data requirement. So they need huge training data requirement, training and testing. So based upon the data, they will train themselves. That is another challenge. So for in the lecture, one technique was mentioned, which is better than the conventional technique. It's also a passive technique, but it is rate of change of what was this? Do you remember what is this rate of change of? What is S and SI? Rate of change of superimposed negative sequence impedance. So here what we calculate difference between two terms and divided by the time difference. So because this is rate of change. So what is rate of change of what? It's rate of change of superimposed negative sequence impedance. So first of all, it's impedance, and it's a negative sequence impedance, and it's a superimposed. Superimposed means we are taking a difference. Negative sequence is Z2. Okay, okay. This is TK plus 1. Or you can take TK or TK minus 1. That can also be done. What is Z2? Delta Z2 is, what is delta Z2?
Post minus pre.
Yes. So, delta 2 post minus delta Z2 pre. And this Z is given by V2 by I2. Negative sequence voltage by negative sequence current. And we have seen in previous last week that how do we estimate phasors? These two are phasors. How do we estimate phasors? What was the technique that we used? Do you remember which technique we used for phasor estimation? So we want to calculate this. For this we want to need this. For this we need this. And how do we calculate this V2 and I2?
DFT, recursive
Yes.
DFT,
Yes.
half DFT,
Yes.
cosine.
Correct. So these are negative sequence voltages. So can we get negative sequence voltages from ABC phases? So from using DFT we can calculate for each phase voltages we can calculate. Even currents we can calculate. Using DFT we can calculate VA, VB, VC, IA, IB and IC. So using that we have to calculate negative sequence voltage and negative sequence current. So we can use this. What we can use? We can use transformation from phase domain. We want to move to the sequence component domain. So negative sequence voltage can be written as phase A voltage plus A square VB plus AVC. Similarly, current also we can find out. So now we have everything from using DFT. So phasor estimation we can do and find out all these phase quantities, ABC voltage and current. Using those value we can find out these sequence current and voltages. Using sequence current and voltages we can find out impedance, negative sequence impedance, which will be just a ratio of voltage by current. So negative sequence voltage by current. So for both the pre and post we can find out, take a difference and then divide it by time. So we'll get the rate. This is the rate. And if this is greater than a threshold, we will say islanding is detected. So is this okay? Although this is also a passive one, but still it's an improved version, and it still it works, and it works at zero power mismatch also. It works for zero power mismatch. But the only problem is the how to decide the threshold value. That we have to carefully decide. Okay. Then the next one is this active active island detection techniques, in which there are two types. One is current injection based, second is positive feedback based. So these are the different example, different types of techniques. Their example. This also you can find in this paper, comprehensive literature survey for islanding detection techniques. And from this, I have taken these many different. Most of them are also mentioned in the slides also in network in the lecture notes. Some few I have added from that paper. So here the advantage of active is we can have negligible non-detection zone, but they have problem because here we are injecting something. We are purposely adding some disturbance, which will deteriorate the power quality. So power quality degradation is a major demerit of this technique, current injection based. Here we can inject any uh, low frequency signal or high frequency signal or even negative sequence signal or pulse signal through the inverter controllers. Then the second one is this positive feedback based. This also provides negligible NDZ, but in some techniques still they have power quality issues. So we can inject any in the example which was shown in the class in the lecture notes. One disturbance was injected in the D axis of a lower frequency 30 Hz. Although signal was of 50 Hz and 30 Hz disturbance
What is
was.
this D axis and Q axis?
This we will actually will see it in future weeks, but main thing is why do these are transformations? Just as we transformed ABC phase quantities into this sequence domain, zero sequence, negative sequence, positive sequence. So this is a type of transformation. Similarly, from ABC we can have another type of transformation which is DQ0. So this is DQ transformation. There is one more transformation which is alpha beta 0. Why do we do this?
Actually,
Yes.
actually, it is direct axis quadrant current and quadrature axis current. While we are designing the synchronous generator, synchronous machines, ID and IQ is main component for designing the electrical machines. For that cases, we are using it.
Uh, that is true. Actually, you are correct. This application of this transform actually started with this machine design only, because there we machine when we are designing, so we have to model them. First, we do simulation, any kind of simulation. For that, we have to make mathematical models. But actually, inside machine, everything is sinusoidal, time varying as well as space varying. With space also things are varying, with time also things are varying. So we are dealing with sinusoids, and dealing with sinusoids is very difficult, especially when we want to control them. Suppose I want to control current, which is a sinusoid, then the controller design will be very complicated. We have to design proportional resonant converters, controllers. So that is a very higher order these controllers, second or third order, which complicates the design. Also, although they will give the correct output, but their design becomes complicated. So to simplify the design, in control theory we have studied, we use what's the most widely used controller. Which one is the most widely used controller? PI, PID, right? But all these controllers, they work with constant input. So we wanted to create something. If sub, that's why the main motive was that if we still want to use PI controller, but with sinusoids we cannot use PI controller. They will give a large error, and if we want to use them, we have to use huge bandwidth. That is very so. That is still after that they will give errors. So we wanted to use PI controller, but also we wanted to get zero steady state error. And PI controller
Sir,
only work with these constant values, DC signals, and actual signals ABC quantities are sinusoids. To avoid this, so we introduce this transform so that we can convert them into this. DQ are these DC signals. Similarly, alpha beta is these are not DC signals. Yes, you want to say something?
sir, I have another one doubt.
Yes.
While we go for current injection based technique, the limitations are it degrades the power quality. So
Yes.
how to overcome the limitation of these cases, sir? Shall
Hmm.
we use some types of power quality mitigating devices because we know how much quantity of current we are injecting to measure the values. So as we know that we can easily use some types of power quality mitigation devices. By the way, we can overcome the limitation, you know.
Yes, that can be done, but for each TG will have to further our protection cost of protection system will further increase with all these things. That is why we have come up with this hybrid. Both passive has a problem of this NDZ, larger NDZ, and this active has a problem of degradation of power quality. So by mixing the two, taking merits of this and merits of both passive and active, hybrid has been developed. So here the power quality issues are very less because what is happening in active continuously we are injecting something, but in hybrid what we will do we will not continuously inject. There will be two layers, we can say two stages. First stage will be that we'll use the passive at first stage. If passive says that there is islanding, then the next stage it will go to the next stage where active will see. So first stage, if it says that there is islanding, then there will be injection. Then only it will inject and it will confirm. So injection is not continuously in hybrid technology, the detection techniques. So that is why we are reducing these power quality issues significantly.
Sir, if it's so, what's the speed of operation in hybrid mode, sir?
Speed of operation same as
It's uh, it's again greater than a passive and active method, you know.
uh, I didn't understand it.
No, no. How quickly it's going to detect the islanding part?
Yeah, this passive and active both are very same frequency. No? They
No, I am asking about hybrid mode.
Yeah, hybrid also that will operate on same. Only thing is it is passive. Still, we are using passive and active. Both are using. We are using. Only
Yeah, yeah,
thing
both
is
are using. Actually,
when
for active, no, initially it has to apply passive. So for passive, it has to take some time, and
yes,
again, it is going to complete uh, active methodologies. So it's also going to consume some time. So compare with active and passive hybrid mode, it consumes some longer time. For protection aspect, as quickly as we are going to highlight the part, is it going to take it as a limitations of hybrid mode?
because it will certainly take a little longer time, but that time is not that significant. Not that much larger because if we see we are doing DFT and we generally take 1 kilohertz frequency, that is a good sufficiently high frequency. So speed of operation is quite high. It's 1 millisecond we are doing everything. So even passive
Okay,
active both
sir.
are working at that speed. So that is
Okay,
the
sir.
minimum speed. Even we can increase a little bit. So hybrid, so speed will not be an issue.
Okay, sir. Okay.
Between first stage and second stage, the delay will not be that much. It will be in milliseconds only. So hybrid so let us see in the. I have slide for each of these. So we'll see. So for this we have discussed passive techniques. We measure and analyze the parameter signal at PCC and then we check whether that parameter is greater than threshold. If it is yes, then we do islanding and disconnect the DG. If it is not greater than threshold, then we do not island. Should we? This is a, so no islanding in that case. But the problem here is these are the different demerits. Concern of determining threshold require a minimum power mismatch, and their performance is also affected by these changes. Then these active techniques. So at active techniques there is an injection, a small disturbance perturbation we call it at PCC. Then we measure and then again do the same thing. And because of this injection there are these power quality issues. And this is the combination of the both active and passive. Or passive and active. The first stage is the passive one and second is the active one. So here we are doing same thing. We are measuring and analyzing the signal at PCC and then check whether it is greater than the threshold value. If it is yes, then do islanding and disconnect. If it is no, then inject the perturbation. And last one is the communication based technology. So it requires any type of communication. So we have seen four different types. One is using PLCC, SCADA can be used, and PMU WAMS wide area measurement system can also be used. But all these they require cost will increase. The main problem with this communication based technology is the cost. These are expensive because entire communication infrastructure need to be built, which we don't have at present. Especially this microgrid we are talking about a distribution system. In our distribution system, we don't have any kind of communication right now. We don't have these communications. So entire the cost of digitizing the entire distribution system, having all these sensor communication, it will be huge. So that's the biggest challenge for these communication-based technologies. So they will activate a transmitter at the utility side and receiver at the DG side. And if the signal is received, then there is normal operation. If there is any interruption, then it's islanding. Problem with this, one of the demerits is, one is cost, second is, what if the communication network fails? Then we will lose the data. We will not receive any signal. We Even the communication system need to have a backup. So even if we are using communication based technique, we will have to use some other kind of hybrid technique also. In case of failure of communication channel, we need to use those other techniques, hybrid technique we can use. So communication technique, always they need to have a backup. If there is a failure of communication, we have to do something. Okay, so now we'll see questions. Today we have good number of questions. So this is the first question. It's a easy question, very easy. So a microgrid has a load of 500 MVA at a power factor of 0.9, and the generation is 500 J 300 MVA. Calculate the power mismatch. So can you solve this, sir? So how are you going to solve? Anyone? Any idea? I guess. So first of all, let us see what is power mismatch. How will you write power mismatch?
PD minus PG.
D, what is D here?
D is
Demand.
demand and
Okay,
Demand
correct.
generation.
So okay, let us write. Okay, PD minus P generation. Okay, so what is similarly it will be, this is for active power. Similarly for reactive power also we'll have QD minus QG. So what is QD here? Oh sorry, PD here.
PD is S into cos phi.
Yes, so how much is it? It's 450. Yeah?
Yes.
And what is PG? PG is 500.
500.
So this is
50 megawatt.
minus 50. I think something is wrong. The options are wrong. And how much is Q delta Q? Yeah, problem. This is 0.95. Okay, to make it 0.95. If it is 0.95, then it will be, what is PD? Or 0.95 PS power factor. PD will be, this is minus 25. What is delta Q? Q mismatch, reactive power mismatch. QD is how much? Anyone calculate?
C is the answer.
C. Yes, C is correct. So phi comes out to be 18.9. So you can write QD as sine phi. And it will come out to be how much? Comes out to be 156. No, QD is 156.12. Take power factor is 0.95, not 0.9. The QD will come out to 156.125. Then subtract it from 300 is QG. So you will get minus 143.875. So C answer is correct. So this we have seen power mismatches, load minus generation. So in islanding, load may not be equal to generation. When we are connected to grid, the grid is supplying the entire load. But in case of islanding, this may not be the case. If there is not sufficient generation within the microgrid, then load generation balance may not be there. Even if the installed capacity, can this happen? Is it possible that the installed capacity within a microgrid is more than the peak demand, but still demand is not equal to generation? Is it possible?
Yes, because of the maintenance activities.
Okay, even if we suppose there is no maintenance activity, so let's say after maintenance, even after removing that capacity which is there for scheduled maintenance, we still have that capacity more than the demand. Then is it possible that demand is still there is a mismatch between power, the generation and demand?
Yes, because of the temperature and because of solar, the PV may not generate the power.
Yes,
So,
the main problem with these renewables are they are intermittent, so it's possible. Even though the installed capacity is much higher, their utilization factor, their capacity factor is quite low. In wind, in some at some location, it is only 15%. So on an average, it is giving only 15% of the installed capacity, which is quite low. Especially for similarly for solar also, we can get only 25-30% capacity factor. That is why they are means in India. Adani has also built one hybrid 600 megawatt hybrid solar wind plant. Also, there is one more project. Its name it's in Andhra Pradesh. So it will be a hybrid solar wind hydro solar wind pumped hydro storage plant. So combining these three, it will be able to firm the output. So even combining solar and wind, we can increase the utilization, this capacity factor of the hybrid plant. It can be even more than 35%. And if we add pumped hydro storage, then it can further improve its capacity utilization factor. So it's possible because of the solar and these renewable intermittent resources. So that is why we this is a challenging task to have a continuous mismatch of load and generations in the islanded mode. So C option is correct. Next question is for a positive active power mismatch. The superimposed negative sequence impedance is zero, negative, or positive. What's the
it
answer?
is negative. We have done this question in the last session. Negative.
On Saturday or session?
Today.
Today was there any other session also?
Yes, 4 to 6.
Okay. So usually the session is in on Saturday.
That was cancelled.
Okay. Okay. Which relay will operate under a high negative reactive power mismatch? This is based upon the NDZ.
Under frequency relay?
Over frequency relay.
So there seems to be a confusion. So how many of you say under frequency relay? And C over frequency relay. So high negative reactive power mismatch. Negative reactive power mismatch means
Yes, sir. C.
P.
PV and QV relationship, we can give the conclusion. Am I correct, sir?
So load is greater
Real
than
power,
generation. Right? Negative
real
is
power and frequency, reactive power and voltage.
no. Sorry. Can you repeat? I'm sorry.
Real power and frequency matching, bonding, and reactive power and voltage bonding. If there is any voltage fluctuations, it will affect the reactive power. Similarly, if there is any frequency unbalancing, real power is going to be mismatched. Am I correct, sir?
Yeah,
No, but
this
this was not correct. Last session we have discussed this. This is only for the transmission side.
correct. This decoupling of P and Q is only possible in transmission system. And why is it possible in transmission system?
Because of
No
R by
idea,
X
sir.
ratio.
Yes, because R by X ratio is very
Low.
low. Correct. In transmission system. So that's how we are able to make those assumptions. And we are able to find out this decoupling. And that is why we have this decoupled power flow also. But in distribution system, R by X ratio is quite high. And our conventional power flow methods, they don't work. And we don't have a direct this relation. So in distribution system, power, both active and reactive power depends on both frequency and voltage. But there is a major relationship also. One thing dominates the other, but actually in principle they depend on both. So this is this graph. This is the non-detection zone. This one, and this x-axis is active power mismatch is, and q-axis is reactive power mismatch. So if there is a positive active power mismatch, that means load is much higher than the generation. So in that case, what is going to happen? Under voltage. It will try to hit the under voltage limit. And this is the relationship. So active power mismatch is majorly governed by this voltage in distribution system. And this Q depends upon frequency. And that is why we have this graph. So if there is negative power mismatch, that means generation is high. And that's why we see, why do we see over voltage issues in distribution system, especially after the solar has been installed. In several places in distribution system, because of, especially during the daytime, when the solar output is at its peak during this afternoon time, they the node voltages, they experience over voltage issues because of high injection, high amount of PV injection. So there are over voltages, and this is showing the same thing. And similarly, if we have positive reactive power mismatch, then frequency under frequency limit will be reached. And if there is negative reactive power mismatch, over frequency limit will be reached. Is this clear? So the relation between the P is related to F frequency and Q is related to voltage. So this always you have to remember that this is applicable at transmission level, and we call
Yes,
it
sir.
PQ decoupling. It's not, we should not apply this same principle at distribution level. And that is why we'll see in the further weeks, subsequent weeks, that the droop characteristics that we have for generators at transmission level, we have this frequency droop characteristics, P and F here. In distribution system we don't have. We will see F and Q and P and V. These two droop characteristics we will see in distribution system. Previous question, is this clear? Then previous question, are you talking about this one? Positive active power mismatch. Why for positive active power mismatch superimpose negative sequence? Okay. So it was also discussed. So who would like to, who can explain this one? Why for positive active power mismatch the superimposed negative sequence is positive or negative? Or it's negative. Why is it negative? So active power mismatch is positive. That means load is greater than generation. And you see, if load is greater than generation, what will happen? Voltage will reduce. Voltage will reduce. Voltage will reduce, then impedance will also reduce. And if we take delta Z, then Z2 minus Z2 pre, because this is reducing. So delta Z will reduce. Is it clear? Is it okay? Okay. Similarly, opposite will happen if there is a negative active power mismatch. So for negative active power mismatch, generation is more. Generation is more. uh, You receive generation is more, and over voltage will be there. Voltage will increase, impedance will increase, and the superimposed negative sequence impedance will become positive. Next question is this: in the rate of change of phase angle detection scheme, estimated rate of change of phase angle deviation in case of islanding is greater than threshold, less than threshold, or equal to threshold. It's a simple question. The principal which
Only greater than threshold only.
is because we have seen in passive detection techniques, in passive islanding detection techniques, it can be any quantity that we are measuring. The its rate of change or the superimposed quantity that has to be greater than the threshold. We saw rate of change of frequency or rate of change of its superimposed negative sequence impedance. So these all should be greater than the defined threshold value. This also we have discussed. So what's the correct expression for rate of change of superimposed negative sequence impedance? Which one?
B is the answer. B. B.
B. B is correct. So we have to subtract from the previous value. So both time and the superimposed negative superimposed impedance. So Z2K minus Z2K minus 1 delta Z2 K and similarly TK minus TK minus 1. Limitation of conventional islanding detection technique. Which one is correct?
All.
And because
Is
they they have this large NDZ, they require a minimum NDZ, and they also no. Is D correct?
C correct, I think.
Result in NDZ. Even B is also correct, but A is not correct, no, because power qualitative degradation is not there in uh,
It should be a large NDZ. Result in NDZ is not a correct answer.
it should be large. So here we are saying conventional means all active and passive both are included here. If we consider that way, then these three will be option. Sorry, A, B, C, D. Or D is the option. I will change this. I will make it large. So it's considering both active and passive. So if it is only active, conventional, if I make it conventional active identity detection technique, then the answer will be C. Result in large end design.
So conventional means except artificial intelligence, all the techniques we have to take. Is it so, sir?
So means even hybrid is not included. Hybrid we are
Oh,
considering.
hybrid is not included. Okay, sir.
So in signal injection based islanding detection technique, injected disturbance signal is what kind of disturbance we can inject.
It's pulse
Low
signal, sir.
frequency.
Which one?
It's pulse signal, sir.
Actually, we can include all. Low frequency, pulse signal is also possible, negative sequence also is possible. So all three are correct. So it depends upon the type of technique which
Sir, actually, in current injection method, we are injecting the current I suffix 30. 30 simplifies lower frequency. If you have to take standard nominal frequency is 60 hertz, only half of the frequency only we are injecting.
correct.
So it may be low frequency,
Yes, it's low frequency. Low frequency is possible. We can use low frequency.
Is it possible to apply negative sequence, pulse sequence also in
Yes,
current injection, sir?
yes, that is also possible.
Okay, sir. Thank
Only
you.
the technique will change, but it will still
Okay,
work.
sir. Okay.
So disturbance can be of any kind. So we use this type of in literature. These type of disturbances have been used to carry out this active islanding detection techniques. So D is correct. And next question, in which mode of operation the fault current in microgrid is high?
C is the answer.
How? Why C is the answer?
It, fault current, it depends upon the location of the fault. So grade is the more appropriate answer, A. However, if the fault is near that the where the relay of ice landing is there, so there also maybe the fault is more, the current may be more. So more appropriate is A, but however it depends upon the where the fault occurs.
Actually, for these, if we compare these two, then uh, for these DERs or DGs,
Sir, it's grid connected mode only.
because yes, why?
Because in grid connected mode, from grid fault current is flowing, from microgrid fault current is flowing. But once if it is islanded, that faulty part is removed from the cases. So only microgrid fault current is only flowing through the load.
Hmm.
So high current means it's only under a grid connected mode.
Is the
Without
main
islanding, if fault occurs, more current will be injected.
yes, because in islanding mode, there's only supplying the these DGs are supplying, and DGs, especially for these inverter based DGs, they have a limit on fault current. They cannot provide very high amount of fault current. Their fault current is limited to 1 to 2 per unit, maximum 2 per unit. So they cannot provide maximum more than this. Their suppose their rated current, they are rated at 50 amperes, so they can maximum provide up to 100 ampere of fault current, not more than that. That's not possible. But those convention generators, those synchronous generators that we have in these our grid, they can provide huge amount of fault current. So these are inverter based DGs. Even if synchronous based DGs are there, they can provide maximum up to 5 per unit. So they have a limit over the fault current. So in islanding mode, the current will be limited because of these DGs, different types of DGs. That is why current in this grid connected mode is quite high. But it may happen that sometimes if number of DGs is quite high, then things it may
So
happen.
practically, if you think wherever this PCC is there,
Hmm.
okay, the reverse power flow cutout is also there because we don't want a huge grid to supply that fault. Okay, so in the theoretical class we don't discuss that. So grid never feed to the small distribution. Small distribution if it is sufficiently generating the power. Say in case there are small microgrids which are sufficiently generating the power in house, so then only access will only go to the grid or small mismatch will go to the microgrid. That is the question.
No, I didn't understand this. Yes. You're saying
Just
yes.
just like the my point is
Hmm.
grid is having a huge power. Okay, so
Yes.
microgrid has a very less power. So there is always a reverse flow mechanism is connected at PCC. That means if the microgrid is self-sufficiently generating, it should feed the load which is there at the microgrid. Access will go there or little bit mismatch is less, then it will come from the grid. That is my point.
Yes, yes, that is true. Microgrid, we
So okay, feeding fault at the microgrid level from grid. Though theoretically it is possible, but practically it will never happen.
no, no. If fault is there, then fault will all the sources will feed that current, and our protection system which isolate the system, it works on that fault current only. If that current is not high, protection system will not work. So since all the sources are feeding that fault current, that is why our protection system, the overcurrent relay, is able to know that yes, the current has gone to a quite high value, the threshold is crossed, now I should trip. So the protection system is designed on this fault current. If the fault current is not high, the protection system will not work. We are able to isolate the faulty section because of this high current value itself. But the problem with distribution, these generators, is that their fault current is very limited, and the present setting of overcurrent relay that we have in distribution system is quite high. Their threshold is much higher than the limit or the fault current that these DG can provide. So that is why they are not able to detect the fault. That is the problem. This is a big problem, that their fault current is limited to only 1 or 2 per unit, 1.2, 2 per unit. And that is why we need to change the relay settings. That is why we are talking about adaptive power, this protection system. So that when the mode changes, in grid connected mode, there is no problem. Grid is also feeding the fault current. We don't have control over who will feed the current. Whenever there is a short circuit fault, everyone will feed the current. It's network. We cannot control. The only way we can control is using the protection system. And it trips only when there is a huge current. So if there is a fault, all the sources will feed the current if there is a path. We don't have a control over it. Is it clear?
Yes.
So that is why we are talking about these challenges. Uh, and as the number of DGs increase, these settings also keep on changing. So it's a big challenge how to keep on changing the settings of these relays. For that, we need communication system. Either we keep a cap on the penetration level in a microgrid, that we should not have mm, the DGs beyond a particular level of penetration, so that we can have our protection system within place. Otherwise, we'll have to change every time. So somehow we have to do something. Either we limit the penetration, or we make the protection system adaptive. So whatever may be the configuration, mode of operation, number of DGs, location, type of DGs, for any situation, the protection system should work. So a lot of research is going on in this area. How can we do this in the most economical way? And it's an open problem. Okay, so let us move to the next question. Next question is, due to bidirectional faults, which type of traditional relay are unable to provide safety protection?
All, I think.
No, here we are talking about microgrids. In microgrids, we don't use distance relay. We do use distance relays in transmission system. So what is the problem with the conventional protection system in distribution at distribution level? And how bidirectional fault current will create a problem?
Then the answer is B then.
Yes, B is correct. But why B is correct?
See, in microgrid, the
Yes.
fault current is bidirectional. So if you put unidirectional over current relay, then it will not serve the purpose.
Hmm. Yes, because just as we saw, our conventional distribution system are radial in nature, and the protection system that we have assumed that the current is only in one direction. Current only flows from the substation towards the load. So whenever if we have a fault anywhere, this the relay will trip, or this may trip, this may trip. They will only trip for a forward fault, and because they have current only in this direction, they are designed only that way. But if we have a generation here instead of BG, then if we have a fault here, let's say fault here, then this will also be current will come from here also. So this relay will also see a current if we have a only over current relay, and the current somehow if it is more than its threshold, then it may trip. Yes. Do you have any question? You can ask. Yes. Devendra sir. So bidirectional power flow will create a problem because they don't this over current relay they don't have a directional sense. They will trip whatever may be the current. If the current is more than the threshold value, they will trip irrespective of the direction. But we don't want that because that will lead to unnecessary tripping. Fault may be in some other feeder and tripping is in other feeder. So that is a problem. We don't want that. So we need a directional element. That is why the overcurrent, conventional overcurrent relay will not serve our purpose in case of microgrids. Next question. Yes, this is the next question. Disturbance current of ID 0.05 IDM cos omega naught D is being injected into the D-axis current controller after islanding the frequencies present in PCC voltage R. So which one is the correct option?
I think C is the correct answer.
Hmm. Correct. C is correct. So if we do this transformation, then we can get this value. So we'll see in the final term these three frequencies will be present. So dq to abc transform if we do, using trigonometric expressions, you can solve it and you'll find these three frequencies will be present. So omega naught plus omega d and omega naught minus omega d, because it will result in cos a plus cos b terms. Which of the following relays are used for protection of distribution network in presence of distribution to distributed energy resources? This we have already discussed. What's the correct answer?
None of the above.
No, why none of the above? Just now we discussed we need something. So in conventional system, distribution system, which relay are we using?
That is distance relays we use.
No, no, no. Essentially we are using for transmission line protection. For in radial distribution system, we use this overcurrent relay. We use these overcurrent relays, which are based on this IDMT characteristics. What is IDMT?
Inverse distance time relay.
No, not time. Oh, distance. Shri Lavanya, sorry, I could not hear you. Your voice was not clear. Can you repeat? Inverse definite minimum time. It's IDMT. It's not distance. It is definite because inverse is because as the fault current increases, it takes lesser time. More the fault current, more quickly the relay will respond. But minimum time, definite minimum time is, it's called DMT because the time of operation is never zero. It cannot respond in zero time. It will certainly take a minimum time, but there is an inverse relation also, that more the fault current, lesser will be the operation time. That is why it is inverse, because of this inverse relationship, and then definite minimum time, because minimum time required for its operation. So this is for the conventional radial distribution system. But if we have these distributed energy resources, solar, wind, then we will need one extra element. What's that? Because we want to distinguish, bi-directional current is there.
Directional we have to include.
Yes, we have to include this directional element. So we should know the relay should trip only when current is in a particular direction. It should not trip for the backward flow. So we need to add this directional element. So the relay will have both these elements, directional also and overcurrent. And when both of these say that yes there is a fault, then only fault will be there. So that this requires an end operation. So both the conditions should be met. The current should be more than the threshold value, and also direction should be correct as per what it is designed. So if both the conditions are met, then there will be trip signal. Trip signal will be generated. So in the directional element, there are two quantities. One is polarizing quantity and one is the actuating quantity or the operating quantity. In directional relay, we are uh, checking the how are we checking the direction in direction relay. What are we measuring or determining to check the direction, whether it's a forward or backward fault? What determines that?
Phase sequence, I believe.
No, not phase sequence. They're close. Means it's phase. It's not phase sequence. It is phase angle. So
Phase
which
angle.
phase?
Phase
Which,
angle positive or negative? Yes, yes.
yes. Which phase angle?
Delta. Delta is ahead of relay or delta behind the relay.
No, but what is that delta? How are we calculating? Suppose I'm measuring voltage and current and all these quantities. So how am I going to calculate that angle? What is that angle?
So again, with the help of DFT, of DFT, and cosine recursive methods, we can calculate magnitude and the phase angle.
Okay,
With the help of
No,
GTS time,
mhm.
phase angle easily we can calculate it.
No, I'm saying this directional element. So phase angle of what? Which quantity are we talking about? So direction relay will take a decision based upon phase angle. But phase angle of which quantity?
Current,
Only current?
current and voltage.
Yes, so we have to take the angle between current and voltage. So which one is the reference here? Voltage or current? So that is why we have these two quantities, polarizing quantity and operating quantity. So which one is the polarizing quantity here or reference? Correct.
Voltage.
Yes, voltage is the reference here. So we take voltage as the polarizing quantity. And why is that? Why voltage is taken as polarizing quantity? Why not current?
Because current is a directional quantity.
Means, means why? Means, directional means is voltage not directional quantity? Means both have
Current is
magnitude and angle.
current is current is okay either load or from generation. So there the polarity may be changed, but voltage is fixed for the bus.
Fault current operating quantity. Yeah, fault current is operating quantity. Actually, the main reason for that is why means if we take something as a reference, that means it has to be there. It should not change. Correct?
Yes.
Yeah. So in when there is a fault, what will change?
Current will change,
Current will
voltage
change.
will be
Voltage will also change. But there is something which will not change. So what will happen? Current. So each phasor has two things: magnitude as well as phase. In current, when there is a fault, both magnitude and phase will change. Magnitude will increase and phase will also change. In voltage, magnitude will decrease, but phase will not change much. It's almost same. So this may be if we consider this as pre-fault voltage, then fault voltage will be like this VF in same phase, but magnitude will be less. But if we have current, suppose this is pre-fault current, then post-fault current can be something else. Its direction will also change. Post-fault current will be very large, and its direction will also be different because it changes both its magnitude and angle. We take current as the operating quantity or actuating quantity and voltage as the polarizing quantity. So we'll measure this angle between voltage and current. This is that angle which we are measuring. So if this angle is between 0 and 180 degree, we say the fault is backward, behind the relay. If we have relay, if we have a fault here, and these are two faults, F1 and F2. So if angle is between 0 and 180 degree, then it will be fault F1, sorry, F2. For this relay R1. And if this angle is between 180 and 360 degree, this angle between voltage and current, then it's a forward fault F1 for this relay R1. Is it clear? Okay. And then one more important thing is this relay coordination. So now we have understood that we need a directional element in addition to the overcurrent relay. So in overcurrent relay, we have one important, even when this direction in conventional system, we have this relay coordination. So if one relay fails, if one relay did not pick up fault, did not detect fault, then what will be done? So if a relay fails to detect a fault, then we have a backup relay. This R1, this is R2. So suppose there was a fault here, F. So for this fault F, if R1 fails, yes, correct. Yes. R1 fails, then R2 will take care of the fault. But the R2 will, there is a delay between R1, the operation of R1 and R2. There is a delay of around 0.3 to zero point 0.5 seconds. So if R1 fails, then after 0.3 to zero point 0.5 seconds, the R2 will trip. So this is the backup protection, and we need to have the backup protection. There may be anything may go wrong. So that is why we keep the backup protection. Is it clear? Even in transmission system, we have backup protection. Backup protection is very important. Even in distance relay, you would have seen this zone protection, zone 1, zone 2, zone 3. That is for distance protection. So if a relay is not able to detect fault within its zone, then another relay a backup relay for that relay will take care of that protection. Okay, so let us move to next question. This is the next. Oh, this is already done. We have discussed this. Huh? Select the correct pair, polarizing and operating quantity for a directional relay. So which is correct? A, B, C, or D? Just now we discussed this.
B.
Yes, B is correct. Polarizing quantity is voltage and operating quantity is current. Correct. This also we have discussed. Angle difference between fault voltage and pre-fault voltage should be equal to. Which one is correct? 60 to 70, 40 to 50, 70 to 80, or 0.5 to 1 degree?
It is 1.
Yes. So it should be, ideally it should be 0, but it should be, if there is little deviation, then it should be as low as possible, as minimum as possible. So this is correct, 0.5 to 1 degree. That is it. Because it's a reference quantity, so it should not change its angle. Because here we are not concerned about magnitude in directional element. We are concerned about angle. So angle should not change. If it is a reference, its angle should be same. Almost it should be same. It should not change. Yes. So questions are over. If you have any doubt, you can ask. We have time, 5 minutes. Anyone? You have any doubts? No doubt. Submit assignment 4, but it is displaying 0. Okay. Did you submit within the time limit? Then it should not happen.
So why in the fault we take the negative sequence current as an indicator of fault?
For which, where should, is there a different methods, different techniques? We can use different quantities for fault detection. Previous दो का answer means which previous two questions? This one? Oh, sorry, since you were asking why are we taking negative sequence current for fault detection?
Yes. And whenever there is a fault, we take measurement of negative sequence current.
Who else for fault detection we see both positive, negative, as well as 0 if it is present. Because actually these negative, positive sequence, these we have created for our understanding, and we calculate them for to. Why did we go to this transformation? These are result of this phase ABC to sequence component transformation. And why did we use this? Because this ABC, we use this ABC when everything is balanced. Three-phase system is balanced. It's not that we cannot do unbalanced system analysis in ABC domain. We can do that. But to make our life simple, to make it easier,
0, 1, 2 is 0 phase sequence, positive phase sequence, and 2 is negative phase sequence.
yes, correct. So when everything is balanced, when everything, all the three phase voltages and currents are 120-degree apart and they are equal, then everything is balanced and we can do entire analysis on a single phase basis, and just uh, then for the rest two phases just uh, make the 120-degree phase shift. because everything, all the magnitudes are same. That's why we are able to do a single phase analysis, and it makes the analysis very simple. But as soon as there is unbalanced magnitude or angle, this changes, then doing this type of analysis, per phase analysis, is not possible. So to do the same kind of analysis, what we do, we convert that unbalanced system, say this type of system, into three systems. We decompose it into three, summation of three systems. One is zero sequence, then positive sequence, same as our this reference, and then one is negative sequence. So if it is A, B, and C, then it will be A, C, and B. So this is negative sequence, this is positive sequence, and this is zero sequence. So we are decomposing this into three. Now we will have three circuits. Here, when everything was balanced, we were making only one single circuit and we were doing per phase analysis. But here we will make three different circuits. Negative sequence will have a different circuit, positive sequence will have, and zero sequence if it is present. If there is a path for zero sequence current, it will be there, otherwise it will not be there. Then we will combine them in fashion based upon the type of fault, and then we can do analysis. So it becomes very easy. That is why we do this type of transformation. And if our analysis is based upon this, then we will need what? We will need both. We'll need all the sequence currents, zero, positive, and negative sequence currents. We'll have to measure them. We have to calculate them. So if we are measuring ABC current, then we will do DFT and then calculate this sequence current from this transformation using this transformation matrix. We can calculate these three. So Fortescue, he gave this concept, and then we used it to make our analysis simpler. But in distribution system, even with ABC, without going to phase, we can do everything on a phase, in phase domain also. But still, we use this concept of with this sequence component to simplify the analysis or to do in between calculations. If you will read this book of Cresting, he has written a book on this distribution system analysis, entire how this OpenDSS software is working. So behind that, everything, the theory which is there, it's given in that book. So entire three-phase analysis, whether it's short circuit, all kind of analysis is done on this in phase domain itself. So that also can do. Because in distribution system we have to model everything. There are so many components. It becomes very complicated. Everything he has done in matrix form. He has given different types of matrices and we can relate everything. Even transformer connections we can include inside those matrices itself. But if we go on transmission level, then we have to, for different type of transformer connection, Y delta, delta Y, this the circuit which we make, the zero sequence circuit, it changes. It depends upon this configuration, whether there is a path for zero sequence current or not. That will determine the circuit during the fault. Is it clear?
Yes, so that is why this, my question is, whenever there is a fault like earth fault, so now there the zero sequence current takes the precedence.
Hmm. Yes.
Otherwise, uh, other fault, this negative sequence takes the precedence. So that means our relays are based on this measurement.
Yes, it depends what we are measuring, what type of protection. When we see the earth fault current. That earth fault relay is there, so it requires the zero sequence current. It measures that. So for complete protection, we need different types of, suppose for the generator protection, if we so we'll have these three relays, three for each phase and one for ground. Four relays will be required for the entire protection. So zero sequence current will be measured by that relay. Ground fault current, that will measure zero sequence current. So depending upon the type of protection, we measurement also changes. So three relays for three phases, and from that we calculate those uh, positive sequence and negative sequence. And for zero sequence, we have these ground relay also. When earlier digital protection was not there, they were using these four relays. They have to measure that ground fault current also. So they used to have another relay for that ground current, so to measure that ground current. But in digital relay, we don't need that, because using this phase sequence transformation, we can do that.
So digital relay, only one relay is sufficient to measure all the sequences.
For a phase, in one relay, we'll be measuring all the three phase current, three phase voltage and currents. So one relay has all the inputs, all the three phase voltages, all the three phase currents. From that, because they are getting samples, it's
But they are connected with all the three phases, na?
yes, the relay will be connected to all the three phases. Yes, it is getting input from all the three phases.
Okay, thank you.
Okay.
Sir, excuse me, sir.
Yes, yes.
Sir, what may be the angle difference in between fault current and pre-fault current, sir? Voltage is minimum, so we have to take 0.5 to 1 degree. What about the current, sir? What is the range?
It can be anything depending upon where the fault is. We saw it can be between 0 to 360 degree. It can be anything. So various that. So if phi is between 0 to 180, it is a behind. It's a fault behind the relay. So it will be this F2 fault. So it can take any value. It depends on the distance, even the ground impedance will depend upon several things.
Okay, sir. Thank you.
Okay, so let us then end the session if there are no more doubts. Shall we end? Okay, so thank you all of you for joining.
Thank you, sir.
Thank you. So we'll meet next Tuesday, same time. Thank you.
Sure, sir. Thank you.